Thanks everybody for showing up. This is cool. I have a number of apologies before I start. This is a talk I'm working on for Scala Days next month, so you guys are my guinea pigs. So I may be looking at my notes more than I would like to. So sorry about that. Also, I'm recovering from a cold, so I'm a little wobbly and I'm chewing on a cough drop. So we'll see how I survive. I am very interested in feedback. So if there are parts of the talk that don't work for you, please let me know, because I still have some time to fix it. So any constructive criticism would be helpful for me. All right. So who am I? I'm Rob. I like to do functional programming in Scala. So this, well, I mean in any language, but Scala is what I use. So how many people here are Scala programmers? Almost everybody looks like, and we can't see the other room from here. So the stuff I'm going to talk about applies to basically any functional language, but the code's all in Scala, and if you don't understand it, just stop me and I'll try to explain it. As Adam said, I'm tpolecat basically everywhere. I'm very easy to find. I work on a lot of open source functional programming libraries in Scala. So I work on a lot of the type level libraries for Scala, if you've heard of those. And I'm a programmer at the Gemini Observatory. So that's what I do for work. And so that's the one of the machines. We have two telescopes. There's one in Hawaii and one in Chile. They're 8.5 meter silver coated telescopes, optical infrared. The line coming out is our laser guide star system at Gemini South in Chile, so that ionizes a star up in the upper atmosphere. And we know that if it's jiggling around, we can correct for it because we know it shouldn't be jiggling. So we can use that to correct for turbulence in the air. So that's what that funny line is all about. So we have a small team and we have a lot of software that we have to maintain. And the software has to be correct. Time on the telescope is extremely expensive, so we can't screw stuff up. And what we have found is that switching to Scala, and specifically switching to pure functional Scala from Java, has dramatically increased the quality of our code and our ability to maintain it as it changes over time. So what I'm going to be talking about is sort of fundamental functional programming stuff. But I really believe in this stuff. I do it every day, and I see the effects of it. So a few more pretty pictures just to show the kind of stuff we do. Let's see. The kind of spooky looking thing on the left is the Skull Nebula. It looks kind of like a skull with glowing eyes, which I think is kind of cool. The galaxies there are called Stefan's Quintet. It's five galaxies. Up at the top, that is Pluto, and the little dot is Charon, just taken at a few different points in time. The images on the right-hand side are of Io. It's the fourth largest moon of Jupiter, and it is just completely just blasting with volcanoes. So all of those dots you see are volcanic eruptions, and we can see that from the ground, which is just amazing to me. So anyway, if this interests you, you want to see more pretty pictures, Gemini.edu is where to look. Okay, and that is all of the pretty pictures. Okay, so the motivation for this talk is that I started going to Scala conferences and stuff about 5 years ago, and people were up explaining what monads are. And everybody thought it was insane, and you couldn't say monad, and people would throw things, and it was like a big deal introducing this idea. And like 3 years ago, everybody was talking about free monads. Last year, everybody was talking about recursion schemes and fixed point types. And this year, everybody's talking about tagless final encoding, whatever that is. And the problem is we're leaving people behind. Okay, monads have not gotten any easier to understand in the last 5 years. We've just stopped trying to explain them to people. So a few of us got together and said, look, we're going to start giving more talks about functional programming fundamentals and try and get more people caught up, because You know, we're on doing fancier things, and they're newcomers who are getting lost. So that's kind of the motivation for this talk. Our goals for today: first, don't panic. I'm going to go through a lot of code, do a lot of code manipulation, and derive a lot of things just basically from first principles. And the goal is not to follow and remember every single step that I take. It's just to understand that these things are connected. They're not arbitrary, and there is a big picture that all this stuff fits into. And as you learn more, you'll start to be able to fill in the gaps yourself. We want to understand what functional programming is to begin with, and why it's useful. This is something that we don't actually explain that often. Gain some insight into the way functional programmers think. I think a lot of the learning curve in moving to functional programming isn't learning the abstractions and the patterns and things. It's just learning to think like a functional programmer. So just showing some examples of code manipulation can help with that. And we want to understand what monads are and where they come from. So this is a talk about monads. If you're a functional programming expert, you understand monads. You may not see anything new, but you might. We'll see. And just be inspired to be curious about this stuff. It's not hard, and it is interesting. And there are a lot of people who are really excited about helping you learn this stuff. All right, so functional programming. What is functional programming? So let's go all the way back to basics. Okay, so we have some values. Okay, and because Scala is a typed language, we divide these values up into buckets by type. So we classify our values by type. And we can think of these types like sets. Okay, we were just talking about Clojure. In Clojure, every syntactically valid program is trivially type correct. So they don't have this distinction. Everything is kind of the same type. It's the Clojure type at compile time. And then you have to look at stuff at runtime to distinguish. Okay, so let's talk about functions. We have functions that map values from one type into another. And this is, we're talking about a mathematical function, okay? So it maps every value in A to exactly one value in B. So this is a set theoretic function. This is the stuff you learn in math. And it's not necessarily clear from the picture, but that's all the function does, okay? It doesn't increment a counter. It doesn't check the system clock. It doesn't write to a file. A function is just a mapping from values to values, okay? Is everybody cool with that? Okay. All right. So such functions are said to be pure. Okay, so and what that means is the output is determined entirely by the input. Okay, mapping from values to values. And the consequences of programming with pure functions are that evaluating an expression always gives you the same answer. Okay, so that means we can always inline a function call. We can always factor one out. Okay, because we know we'll always get the same answer. Okay, more generally, we can always, I'll just read this. We can substitute a variable for the expression it's bound to, or introduce a new variable and factor out a common sub-expression. And this property of expressions is called referential transparency. And it's just this simple idea that's the basis of all the good stuff that comes from functional programming. So let's look at some examples. Okay, so the question here is, are these programs the same? And if you may not be close enough to read that, I'm sorry, I can't make it bigger. So program 1 says we have some value A that's assigned to, it's bound to some expression, to some arbitrary expression. And then we form the pair of A and A. Is that the same thing as forming the pair of that expression 2 times? Can we inline that A? So are those the same program or not? So it's a simple question, and in functional programming, the answer is always yes. They're always the same program, okay? But in general, in Scala, which is not a pure language, it depends on whether that expression is referentially transparent, and that is, in fact, the definition. So let's look at some examples here. Okay, so how about this program? The first one, val a equals 42, and the pair AA versus the inline version, 42, 42. Are those two programs the same? Do they mean the same thing? Yes, they do. Okay, because 42 is just a pure value. Okay, what about this one? So iter is some iterator. So we call next on it in A and make the pair of that result. Okay, are those two things the same program? No, they're not the same program, right? Because the second program will advance the iterator twice, and the first one only advances it once. So what that means is this expression iter.next is not referentially transparent. Look at another example. Print line high. Okay. If you don't know Scala, this might look weird. Print line returns a value of type unit. There's no such thing as a void method in Scala. Every method returns a value. So the question is, are program 1 and program 2 the same? And obviously they're not. The second one prints high 2 times. Okay, so this will end up being a property of essentially any method that returns unit. The only purpose of such a method is to side effect. Okay, let's look at another one. This one is a little subtle. You construct an array and return it twice versus constructing 2 arrays. Are those the same program or not? Any opinions about that? A little tricky. So it's pure as long as you never mutate the result. If you have code later that mutates one or the other of those arrays, then you'll be able to observe after that point that they're not the same reference to the same array in memory. So this is kind of a tricky area, and we try to avoid stuff like this. It might be pure locally. It might not be pure forever as your program evolves. So you've got to be careful. The compiler doesn't really help us out with this kind of thing. So we have to think pretty hard about whether things are pure or not. But once we convince ourselves, we get a lot of freedom. All right, so let's review. So every expression is either referentially transparent or it's not, in which case we call it a side effect. Okay, it's either one or the other. Okay, so that's the definition of what a side effect is. It's just the absence of referential transparency. Okay, and the interesting thing here is that it is a syntactic property of programs. It's something that tells you whether substitutions like those we were just talking about are legal or not. Okay, so saying something is a side effect is only indirectly a statement about the runtime behavior of the program. It's really a statement about whether these substitutions are legal or not. Okay. So if you think in these terms, I think it's pretty straightforward to understand what's a side effect and what isn't. Is can you factor this out? Can you inline it and do so freely without worrying about whether it's going to work or not? Now, why do we care about this? So we care about these substitution rules for expressions because in functional programming, that's kind of the world that we live in. In FP, we're not in the world of statements anymore. We're in the world of expressions. So a functional program is an expression. And running a functional program, executing a functional program, is a process of reducing an expression to a value. Okay? And we reason about our programs by substitution rules. And we build bigger programs out of smaller programs by composing them. Okay, and that's all we've got, and we build everything up from there. So, because all we have so far are functions, let's talk about function composition. Okay. All right. So here's our function again, our function f from A to B, and notice that the function doesn't necessarily have to cover all of B. It just has to map everything in A to something in B. We can create another function, g, that goes from B to C, and knows that g has to map every element in B over to some element in C. Okay, and now we can compose these functions end to end. We can say f and then g, and we get this new function that kind of passes through, that goes from A through B over to C. So it's just function composition end to end. We apply F and then we apply G. Is everybody cool with that? Okay. So what does this look like in Scala? So we can write and then. And so here's a method. It takes 3 type parameters, A, B, and C. It takes 2 value parameters, a function from A to B, a function from B to C, and it returns a function of type A to C. And we do that by taking an A and applying G of F of A. And that's all there is to it. Okay, so that's how we can define function composition. And it turns out that's the only way to write it that will type check under a reasonable set of rules. So because we're in the world of expressions and we're interested in substitutions, we have a binary operator like this. We might ask some questions about what kinds of algebraic properties it has. So for instance, is and then an associative operator? Because if it is, if F and then G and then H is the same thing as F and then G and then H, that gives us another substitution rule that we can use when we're working on our programs. So how do we figure this out? Well, we'll do some equational reasoning. We'll use the substitution model of evaluation and just expand this stuff out and see if it's associative. Okay, so let's look at the right associative case. So if we, and I'm writing this in infix style, okay? So the method is just written as a flat method, but I'm writing it as infix, so I hope that doesn't confuse people, just to make it easier to read. So if we inline the outer and then, we get A to G and then H of F of A, and then we inline the inner one. So A to B of H of G of B applied to F of A. Now we can just substitute F of A for B, and we get A to H of G of F of A, which seems right to me. Seems like that seems good. So let's look at the left one. F and then G, same thing. We inline the outer one, and then we inline the inner one, and then we can apply A and substitute A in for B, and we get the same thing. Okay? They reduce to exactly the same thing. Okay, we proved it. It is, by equational reasoning, this is an associative operator. We got a proof for it. So that's awesome. And now we have a new substitution rule. Anytime we see F and then G and then H, we can change the associativity, and we know we're going to get the same function back. It's going to do the same thing. So this is cool. So purity gives us this fundamental ability to inline and factor out stuff, and we can use that to define, to discover other substitutions like this one. And this is where FP becomes very, very powerful. All right, so what else could we ask about this? So it's a binary operator. We might ask if it has an identity. So my conjecture is that if you have F and then some function that does nothing but return its argument, that's an identity. It's the same thing as the original function. So let's try it. So let's make an identity function parameterized on one type, and it returns a value from A to A for any type A, and all it does is take the A and return it. And if we want to see if it's an identity element for n, then we have to check it on the right and on the left. So let's look at that. So right identity, F and then ID. Let's expand it out. So A to ID of F of A, but ID is just some function B to B. We apply that to F of A, and it's just F of A, which is just F. Okay, so right identity works. F and then ID equals F, and if we do left, I'll go through it really quickly, we get the same thing. Okay, so now we have another substitution rule. Okay, so we know that if anybody says something and then ID, we can just delete the last part because we know that it doesn't change the meaning of the program to do so. Okay, and again, we proved it. Okay, there's no doubt that this is true. Okay, so so what do we have here? We've got functions between types, and we have an associative composition operator. We have an identity element at each type, which is that ID function, and we proved that all this works just by the definition of function composition. Okay, and because there's only one way to implement function composition, everything we've done so far follows directly from the types. This is the only possible consequence. Now, it turns out there's a mathematical structure that describes exactly the situation that we're in right now, and it's called a category. So we draw category diagrams like this, and the category has four things. Okay, so we have objects. So we have these dots, A, B, and C, and in this category, the objects are types. We have arrows, sometimes called morphisms. In this category, they're pure functions between types. We have an associative operator that allows us to compose arrows, and in this category, it's the and then operator. So that's where this arrow comes from. We have an identity element at each object, which is our ID function. So ID of A defines a family of functions for any type A. Okay. So all right. So this is cool. Why do we care? We care because math ends up being useful. By identifying these connections between types and programs and mathematical structures, we have been able to do a lot of really amazing things in functional programming. And I think one of the benefits of FP is that the distance between theory and practice is very, very narrow. We can take these mathematical ideas and apply them very directly to what we're doing, which is really cool. If you're writing code in Java or something, it gets hard to see how this stuff is relevant. This is where we start to see the benefits of doing things this way. We can be more confident that our programs are correct because we can start to define what they mean very precisely. And we can refactor confidently because we have these substitutions that we can identify. So it helps our programs start off correct. But really, the big value proposition of functional programming is that we have these substitutions that allow us to manipulate our programs and refactor very aggressively to keep our programs correct as they evolve. And for me, that's been just a huge lesson of starting in with functional programming. But in exchange for this, we've lost a lot of expressiveness, right? We have this sort of very rarefied view of computation. All we have are like values and pure functions, right? And so how do we square this with the kinds of things that we run into in the real world? So what about partiality? Functions always have to return an answer if they're pure functions. You can't have have something that returns some null value or something, or just doesn't return a value. But sometimes we need to express partiality. So how do we do that? Exceptions, right? We're in the world of values. Values don't throw exceptions, okay? But things do go wrong in the real world, so we need a way to talk about that. Non-determinism. So functions have to return exactly one answer. Sometimes you might want to return more than one answer or no answer at all. Dependency injection, okay? So sometimes we have computations that depend on things that we don't have yet, that are going to be given to us later. We need a way to talk about that. Same thing, logging. Sometimes you want to not just compute a value, but you want to record some sort of chronicle of what's happening while you're computing the value. We need a way to talk about that sort of thing. Mutable state, obviously, there's some kinds of problems that are easier to express in terms of mutable state. And we don't have that, we just have values. So what do we do about that? And imperative programming generally. There are a lot of things that we do when we're programming that make sense to define as a series of steps. You do this, depending on what happens, you do this, depending on what happens, you do this, and so on. So we need a way to recover all of this stuff. We need a way to talk about this without losing the benefits of functional programming. And the way we do that is to use effects. And that's what I want to talk about tonight. Okay, so effect is a really vague term. And that's okay. We're trying to capture an idea that's sort of outside the language. If there's one thing to take away tonight, it's that effects and side effects are not the same thing, okay? It is very unfortunate that they sound the same, but they're not the same. So effects are good, side effects are bugs. So what I want to do is talk about 6 of the effects that are kind of the first ones that you learn when you start doing functional programming. There are lots and lots of effects that we can define. There are lots of ways to categorize them, but we've got to start out simple. So that's what we're going to do. So what we're going to do is talk about these effects and what they mean and what they have in common, and we're going to try and come up with a way to talk about them, about what they have in common in a very precise way. So let's talk about option. So what do we have? We're all Scala programmers mostly. So option is an algebraic data type. It has 2 constructors. One of them is none and one of them is sum. And the intuition is that it lets you define functions that might not yield an answer. So we have an A to option B that will either return you a B, some B, or none. Okay, and we have function G from B to option C. The problem is we can't compose those functions together. Because the types don't line up. And what would it mean to compose those together? Well, if you wanted to get a C back, you would have to get a B back. So really, what it does is it lets you compose this partiality, so that if we could say F and then G or something like that, what we would get is a function that only returns a value if both F and G return values. Okay? But we can't do that because and then won't type check. Some of you might know how to do this, but we're gonna keep going. We're not gonna do it. Let's talk about either. So either is another algebraic data type, but instead of having none and some, it has left and right, and by convention, left is used to report sort of a reason for the failure, and right is used for the success value. So the intuition for this is if you have a function A to either string B, for instance, and G is B to either string C, these are functions that can either give you an answer or they can fail and tell you why by giving you some string description. But again, we can't compose them together. And so what would it mean to compose these together? It's kind of the same as with composing these option functions that we saw on the previous slide. In order to get an answer back, in order to get a C back, both F and G would have to succeed. But if one of them fails, you're going to get that first error back. Okay, so it kind of has this idea of throwing exceptions. The first failure will stop the computation, and that's what you'll get back. And that's necessarily the case, because if F fails, then you don't have a B that you can pass on to G. So the only thing it could do is stop at that point and give you the first exception or the first failure reason. But we don't know how to compose those. Now let's talk about list. So list is another algebraic data type. It's either nil, which is the empty list, or it is a pair of a head and a value and a tail, which is a list. So it's an inductively defined data type. And the intuition we have in FP about list is a little different from what might be obvious or might be intuitive initially, is we think of lists as a kind of non-determinism. The idea is we can have a function that can return many values. So if we were able to compose F and G together, the idea is that what we would get back is every possible C that could have been computed. So every possible B might give rise to a bunch of possible C's, and we want to get all of them back. Okay, so this gives us a way to talk about a kind of non-determinism. Okay, let's see, how many was that? That's 3. Let's talk about reader. So reader is a type that you might not have seen before, and it's really just a wrapper for a function from some type E to A. And the idea is that it's just some computation that needs a value. So E is for environment. It needs some sort of configuration in order to compute its A. So if we had a function A to reader of config B, and then G, which is B to reader of config C, the idea is, and we'll see these are, it's almost just a kind of currying. It's equivalent to A to config to B. The idea here is that if you apply F, if you give it an A, you'll get back a computation that can be completed once you give it a configuration. Okay, and the idea here is if you were to compose them, well, actually I have an example of that. Say type host is equal to string. We have a path function that takes a string and it returns a reader of host to string. So what it says is you give me a path and I will give you a computation that will that'll give you a URL as soon as you tell me what the host is. You can tell me that later. Okay, and there are a couple examples of we'll call path once and then we'll run it with a couple different hosts and we'll get different paths back. So so back to what we had before, we can't compose these things, but the idea, the intuition here, if you were to compose them, the idea is you would have something from something that would compute a C as soon as you gave it a configuration. So you would want to get back something that would sort of thread this configuration through the computation. So this gives you a notion of dependency injection. If we were able to compose functions of this type, then we could define these computations that are dependent on resources that we don't have yet, and we can still compose them. And at the end of the world, we can give them the configuration and actually compute a result. So if there's reader, there must be writer. Let's talk about writer. Writer is an interesting class. It's kind of strange. It's a pair of some type W and an A. And the idea is it's a computation that computes an A along with some information about what happened while it was computing the A. So here's an example. If we say we have a log type that's a list of strings, and we have a toDouble method that takes an int, it can say, okay, I converted n to a double and then return the answer. And then when you run it, you get the answer along with some information about what happened while it was doing the computation. And that's pretty straightforward. But if you compose these, what you would want to do is get back a log of the entire computation from A to C all the way through. So you need some way to combine the logs that are generated by F and G. Okay, but again, we haven't defined how we can compose these things together. Okay, and this is the last one. This is the hard one. Let's talk about state. So the idea here, so state is another just wrapper for a function. It takes a function from some state type S to a pair of the answer and a new state. So the idea is that we define stateful computations as a state transition. We take some starting state, we compute a value, and we return that value along with what the new state is. So let's see, I think I have an example of that. Yeah. So we have a counter type that's an int. So let's make a greet function. It takes a name and then it returns a computation that depends on a counter. So the answer is hello, your person number, whatever, and it tells you what the count is. And it also increments the counter before returning it. So if we say we want to greet Bob and then we run it with the initial state of 1, we get hello, Bob, your person number 1, and the new state is 2. So that's what we should use on subsequent computations in this type. Okay, so the idea here, the intuition is that these are computations that thread state through. So before, when we were talking about reader, we could have computations that take some environment and all the answers could depend on that same environment. This is like that, but you can depend on that state and compute your answer and then pass a new state on to the next guy. Okay, but again, we don't know how to compose these. So we've got a lot of stuff that looks kind of the same, but not quite. So let's talk about what these things have in common. The big thing is that all of these guys, all of these types that we've talked about, they compute some answer, but there's some other context associated with it. There's some other information or some other meaning that's sort of ancillary. It's not part of the answer, but it's something that goes along with it. Okay, and that's what we call an effect. but that's not a very satisfying definition. So let's see if we can be more precise about what these things have in common. So an observation is they all have the same shape. So they all have some shape. There's some type constructor that takes a single type parameter. So we can say f of a equals option a or either EA for some fixed type, for some fixed error type. Same thing, we're reader, writer, and state. We have to fix the type of the environment or the log or the type of the state. But once we've done that, there's only one free type parameter. So all of these things end up with that same shape. Okay, type constructor that takes a single parameter. Does that make sense? I think sometimes partial type application is hard to grok. Any questions about that? Okay. So an effect is whatever distinguishes f of a from a. It's probably still not a very satisfying definition. Mount Rainier looks awesome, by the way, out the back window. Okay, so an effect is sometimes called a context, which I don't really like, but you'll hear people say that. There are tons and tons of effects that we can model with different levels of expressiveness, and these are just the first ones that you learn when you're picking this stuff up. And all of these have a similar amount of expressive power. And that's what we're going to talk about for the rest of the talk, is what is this expressive power? Yes? Oh yeah, the question is why don't I like calling it a context? I think it's because context is kind of overused. People use it for lots of different things. It's become kind of overloaded. You have an execution context. You have this, and people will sometimes think of a context as sort of a dependency injection sort of idea, and it's as we've seen, we can model that, but it's a little more general than that. But you will hear people saying that, and I don't have a strong objection to it. Now, because effectful value sometimes takes too long to say, we sometimes call these things programs. Okay, so f is the effect, and we'll say if we have something of type f of a, we'll just say this is a program in f that computes a value of type a. Okay, so it might seem kind of weird to think of something like option string as a program, but in the general case, you're going to have a more complex type, more expressive type, like reader or state or something like that, where it might seem a little more intuitive to call it a program. But it's a good generic way to refer to these things, and you will often hear functional programmers just saying, I have a program, and programs are just values in this case. Okay, but they don't compose, as we've seen. So let's go back and look at an example with option. So we have char 10, which is a function that takes a string and gives you the 10th character if there are at least 10 characters. We have another function, letter, that takes a character and returns an option int. And let's see, what am I doing? Saying if it's a letter, give me the character code as an integer. Otherwise, give me nothing. And if I try to compose those with end-then, I get a type error. So what we want to do is try and figure out what the game is. What can we do to make these functions compose end-to-end the way we want to? Because if we're able to do this, then we'll be able to build bigger programs from these smaller programs. So let's just ask what it would take. So here is the diagram we saw before. This is just a normal pure function composition. So the question is, what would it take? What would this diagram look like if it was instead of just pure functions from type to type, it's functions that compute programs in some effect that compute types, the destination type. Really, the only difference is that instead of our arrows being from A to B, they're from A to F of B. So let's just make that change and see what happens. Okay, so let's look at this diagram. All our functions have changed. So we have F is A to F of B, G is B to F of C. Instead of and then, I'm using a little symbol that looks kind of like a fish, okay, just to distinguish it from what we've seen before. The ID, when we're doing this, the ID function is usually called pure. And the idea is that it's taking some pure value and somehow turning it into a program that computes that pure value. Okay, so what would we do now if we wanted to define this in Scala? Okay, how would we write this down in Scala? So I think we would do something like this. We create some type class, and I'll call it Fishy because we have that fish operator. It's parameterized over a type constructor, something like list or option or either string. And it has these two operations. We have pure that takes an A to f of A, and we have this fish operator that takes an A to f of B, a B to f of C, and gives us an A to f of C. Okay, so we're just reading the stuff off the diagram and writing it down in Scala. And we can actually start to implement that fish operator. So we know we have to take an A. The only thing we can do with an A is apply F to it, and that gives us an F of B. So now we have an F of B and a B to F of C, and we're kind of stuck. We can't really do anything yet. But we have an F of B and a B to F of C, and we want an F of C back. So is there something from Scala's standard library that might work to do this that you've seen before? It looked like flat map to me. So really the fish operator is a derived operator. What we really need to define is flat map. Okay, so flat map takes an f of A to f of B, and gives us an f of B back. And then once we have that, we can define the fish. And so what we can do is we can add that fish as syntax, as an infix operator for function types. If you look at that, can you understand it? Do I need to? I'm happy to talk through it if you don't follow that. I don't know how much Scala you guys know. The idea is that given any function f from A to f of B, I will add a new method called fish operator that takes a B to f of C and evidence. It takes a fishy. It takes evidence that we have defined this fishy class for type constructor f, and it will give us back an A to f of C. And we do that just by delegating to that flat map method. Okay. So now we have that as syntax, and we can define for option. We can define a fishy instance for it. So pure of A is just sum A. We'll just take a pure value and turn it into an option that computes that pure value. And then flat map, we'll just delegate to flat map in standard library for now. And now char 10 and then letter doesn't type check, but char 10 fishy does type check. Okay, and now we can call it. We can call it on foo, we get none. We call it on this long string, and we get whatever letter has character code 117. And then if we call it, if we call it on one where where that character is not a letter, we get none back. Okay, so we were able to compose those two functions. The effects composed. Okay, so now we've sort of defined how we can build bigger programs out of these little ones. But one of the problems is we forgot about the category laws. Okay, so remember, it's not just anything that type checks, right? We have these laws we have to satisfy. So we have a left identity. So pure into f has to give us f back, has to be the same thing. F into pure has to give us f, and then it has to be associative in both ways. Okay, and we have not checked that. Okay, so we need to do that. So how do we do that? Well, equational reasoning. So what do these things mean in terms of flat map? Let's just expand on them and see what we end up with. So the rule is pure fishy f has to be equal to f. So we just inline the fishy. So A to pure A flat map f has to be f. We can A to expand f. So f is just a function. So A to f of A is an equivalent function. Okay, and then we can just treat A as a free variable. We don't really care where it came from. So now we have pure of A flat map f is the same thing as f of A. So that's one of the rules. Okay, and then right identity, we inline that. F of A flat map pure equals f. Again, A to expand it, so A to f of A. And we can just not care where A came from. Or really, we don't even have to care what f of A is. It's just anything. So any M flat map pure is the same thing as M, okay? So pure is an identity with respect to flat map. All right, let's do associativity now. So left associative composition. We will inline the outer fish, and then we will inline the inner fish. Okay, and then let's see, what can we do? We can substitute A. Okay, so now we have A to F of A flat map, G flat map H. Okay, and that has to be the same thing as the right associative one. So we inline the outer one and the inner one, and now we can not care where A comes from or what F of A is. And now we have this new rule that says M flat map G flat map H has to be the same thing as M flat map B to G of B flat map H. So it just means the flat map has to be associative. It's just there's not a pretty way to write that in Scala. Okay, so we have these rules now. Okay, so we have these two operations, pure and flat map, and 3 laws telling us how they have to relate to each other. And this isn't something arbitrary, right? These follow directly from the category rules. Okay, they're analogous to the rules for plain function composition that we derived earlier in the talk. Okay, and I'll tell you what we've been doing. This category is called the Kleisli category for F. This is the Kleisli composition operator. So when you hear people talk about, if you've ever run into the term Kleisli in functional programming, that's what we're talking about. Okay, so this Fishy type class that we derived using nothing but math is, of course, monad. That's where it came from. Okay, and we got the laws too. Okay, we've derived the monad laws from nothing. So we got the whole thing. Okay, everything you can say about monads is on this slide. Okay, everything else that we do with monads follows from this. Okay, and it all follows from the rules of composition that we learned in our first 5 minutes of thinking about category theory. So I think that's really cool that this stuff comes out of nowhere. So now you know where monads come from, and you know that being able to compose these effectful functions end to end is a useful thing to do because it allows us to build bigger programs. Okay. Now, an important point is that unlike the rules for function composition that are true, necessarily true just based on the type, that's not the case in general for the monad laws. They are a requirement. They're not necessarily true. So when we implement monad, you can't just satisfy the type and call it good. You actually have to prove that these laws hold. And both CATS and ScalaZ provide some really cool machinery for doing these proofs automatically and for running a huge number of tests against your data to establish that your monad instance is probably lawful. So you got to do it. Very important point. All right. So we have pure and flat map that are abstract, and we can define some other operations in terms of them. We can define map. Okay, so we can define map in terms of flat map and pure. And I don't have time to derive the functor laws today, but if you know what they are, you can go through the same exercise we just did, and we can show that this implementation of map has to be correct. It is necessarily correct if pure and flat map are correct. Okay, so if you know the functor laws, and I can talk about it with you afterwards if you're interested in how to prove this. What else can you define? You can define this tuple operator that's useful, that takes an FA and FB, and it gives you an F of A and B. And it's just defined in terms of flat map. And again, if you understand what applicative functors are, you can define app in terms of map and tuple, and again, you can prove that the laws are satisfied. Are necessarily satisfied by substitution, assuming pure and flat map are correct. So I'm not going to go into that tonight. So carrying on, we can make a syntax class that adds these methods to any monadic value. So this is just a syntax class that says if you have an F of A and evidence that it's a monad, we can add those methods to it, and we can derive a few things. So I call these left shark and right shark. The idea is that you've got what you do is you tuple A and B, and then you throw away one side or the other. And I'll show you in a few minutes how we how we can use that to do something interesting. All right, so knowing all this, let's look at our effects again. Talk about option again. We have option. We can create a monad instance for option. So we can define pure, we can define flat map. Now notice, you could define flat map so that it always returns none, and it will type check, but it will be wrong. And if you don't check the monad laws, then you will have an invalid instance and nothing will work. The substitutions that should be legal will no longer be legal. So very important to check. So we're Scala programmers, most of us, and we've seen option in for comprehension. So I'm going to talk about using for or option with the tuple operator. So we have a validation method that takes a string and it validates that the string is non-empty. So we can validate Bob and tuple that with validate Dole, and we get we get a sum back that has both strings in it. If one of them is empty, then the whole thing is none. Okay, so the effect is being composed even though the values are not. The same way we can validate Bob and forget about the answer and validate Dole, and we'll get some Dole back. We can do the same thing with an empty string, and we'll get none back. Okay, so the computation on the left is there only for its effect. Notice we can say validate Dole and validate Bob and reverse the direction of the shark, and we get the same answer back. And the reason for that is that option is actually a commutative monad. You can't do that in general, but you can do it for option. All right, let's talk about either. Again, here's an instance. You'll just have to trust me that it's right. We can create a validation, give it a tag and a value, and it will either, let's see, if the value is non-empty, it gives you the value. Otherwise, it says that the value is empty. Okay, so we can write a program, validate name. We can ask it to validate the first name and then validate the last name and yield a string with the composed answer. And we can see at the bottom that if we validate it, if there's an empty string, then we get nothing back and a message about which string was empty. So it says last name is empty. All right, talk about list again. And I'm just going to speed through because I think we're running late. So let's talk about this tuple operator with list, which is interesting. Everybody's used list in a for comprehension. So let's see what this tuple operator does. It gives us the Cartesian product. It gives us every combination of answers. So this is kind of what we were talking about before. If we have something that computes a bunch of answers and something else that computes a bunch of answers, and we want to combine them, we'll get every possible combination of answers back, which is what we get: 1x, 1y, 2x, 2y, 3x, 3y. And notice that the shark operators, if we say 1, 2, 3, right shark list xy, we get back xy, xy, xy. Because what we've done is we've dropped the numbers. We've forgotten about the numbers. We don't care. It's there for the effect, though. If we reverse the sense, we get x, 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 y, y, y. So the answers are not the same when we reverse the shark. Okay, and the reason for that is that this is not a commutative monad, and they're not in general. We'll talk about reader. Again, I'm going to skip the implementation and just show you an example. We have two functions. We have two methods, one that takes a path method that takes a host, and we have a host length operation that takes a host and gives you the length of it back. And we can compose these and say, first thing we're going to do is we're going to get compute a path for foo bar, and then we're going to get the length, and we're going to compute a string that tells us what the path is and its length. And when we run it, what we get is both of those computations get to look at this google.com. Okay, so we get the path, we get the google.com filled in the path, and we get its length. So both of those independent computations have been composed, and now they both have access to that same environment that we're passing in. So that's our dependency injection. Let's not talk about writer. I have to explain monoids before we can talk about writer, so I'm going to skip that one. Now let's talk about state. This is the last one. I am going to skip the implementation because we're running short on time. But here's a computation for random numbers. What it does is it takes a seed. So this is a computation that gives you a random int. It takes a seed, it computes the next value, and it returns that value along with the new seed, which happens to be the same value. And then we can have another computation that will roll a 6-sided die. It'll take this random computation, and it will restrict it to values between, 0 and 5. It should be 1 and 6. I should add 1 to it. But now we can use that computation twice. We can calculate 2d6 plus 2. So for A coming from d6, B coming from d6, yield A plus B plus 2. Okay, and these things are values. People are puzzled by this, that we can have this value that we can use twice and we get different answers from it. And it's because there's a function inside that that's being run. So we can run this thing. We can run it with the seed value of 17, and we get 10 back, and then the new seed. We can do this for comprehension and run that and get the answer back, and it gives us 2 different values that have been computed. And then we can also tuple it, and we can get two of these composite die rolls. So we can compute this. We can compose this program this way too. We get 4, 7, and then the final state back. So this one is a little hard to follow, but you can use this to do stateful computations, and the state silently gets threaded throughout your computation, which is pretty cool. All right. Well, okay. So is that it? No, not at all. This is just kind of a taste of the kinds of effects that you can model. These are just kind of the basic ones that you learn to get acquainted with this stuff. And monads that we've been talking about are just one family of effects. So monads describe they describe the compositional properties of families of effects. They just happen to be really fundamental, which is why I'm talking about monads instead of other things. But it turns out the operations we've talked about sort of form a hierarchy. There are lots of things that have this map operation. There are fewer things that have zip, still fewer that have map, zip, and pure, and then fewer things that have all 4 of those operations. And so in Scala, we represent subtyping, or we represent subsets of subtyping. So what we've gotten a taste of really is functor is what gives us map, apply gives us zip, applicative gives us pure, and monad gives us all 4 of the operations that we've been talking about. And these are kind of the first families of effects that you might want to learn about, but there are really quite a few more. This is from Cat's core, and this is just a subset of what's in Cat's core. So there are lots of different ways to categorize these effects and their expressiveness. And that is all I've got for tonight. Thanks.